So welcome everyone to the database seminar on Bitcoin and blockchain. And today Shaz Kadir, yes, from Microsoft, will talk about how to program blockchains.
Thank you, Dan, and thank you, Shumo, for inviting me. This is by no means a polished talk. When I accepted Shumo's invitation, I told him that I think of this as basically leading a discussion. I have only about 10 slides in my presentation, and I'm hoping that each slide is going to be dissected and destroyed as I go along. So I'm looking for just getting feedback and getting a discussion going. So a brief introduction about myself. My name is Shaz Kadir. I worked in MSR until for many years, and on July 31st last year, I moved to Azure Blockchain. We have a small team, about, at the moment, still less than 10 engineers. Yes?
Where is Azure located?
In Redmond. Yeah. Still less than 10 engineers. And we are growing aggressively. We are looking for talent in systems security, programming languages verification. If you're interested in cutting-edge software development, let me know. Okay. So this is a database seminar. And one question that always comes up is, why is the blockchain special? And really the question underlying it is, what makes it different from a database? We are so used to building applications on top of database. Databases offer transactions. They offer a programming model based on, SQL, which is mostly declarative when you are querying data, and there is some mishmash of imperative features in it for updating tables and whatnot. So why do we need blockchain? So these are the questions I was asking myself during the first 3 months of joining my new team. Before that, my expertise, I work in the areas of programming languages, compilers, testing tools, verification, and I knew nothing about blockchain. So I spent quite a bit of time trying to answer these questions for myself, and trying to figure out why is there so much excitement in the community about it. And here are some things that I outlined, some conclusions that I outlined for myself. And I want to see if you guys agree with that. So in a database, data is central, right? Because the data is stored inside the database, everybody agrees on the data. In the blockchain world, the code is central. It's the shared code that a bunch of parties who may not necessarily trust each other, they agree to execute that code, and that is the shared source of truth. So unless you reason about the code and you argue that, yeah, it is doing the thing that we all agreed to do, it doesn't help you. So just by putting, suppose your code is garbage, it does not achieve your end objective. By putting it on the blockchain, it is not going to give you any benefit. So I think that this focus on the code that is achieving a business objective between two parties that may not mutually trust each other is kind of a new thing in the blockchain space, right? The second thing is that we all know that in blockchains the programming model is transactional. So the blockchain receives transactions that are coming potentially in a distributed system from all over the place. It serializes those transactions and commits them on the blockchain in some arbitrary order. So that is something common with databases, but it's also true that the programming model is also event-driven and imperative. If you look at the kinds of VMs and programming languages that are in use today, the most popular one is Ethereum. Ethereum has this idea that a transaction comes in. A transaction is basically a message handler, right? And the code for it sort of executes, right? And it's imperative code. There's state inside the system, and then the state gets updated by code that looks like if conditionals and while loops and method calls and so on, and then it terminates. And Because it has that state could be unbounded, and because you can have loops, you can very easily write Turing-complete calculations. And in a world where anybody can submit transactions, you have to worry about termination of all this. So there are all these other things going on about artificially restricting the length of computations by using gas and so on. So this is all testament to the fundamentally imperative nature of the programs that are being written here in the blockchain world. And finally, the most important thing is that you always have to account, because the parties that are executing this code, they may not necessarily trust each other. So there's always the possibility that a dispute will arise, right? And to resolve disputes, what we want is a log of what happened in the computation. And we want to make that log replayable, right? So that we don't have to trust the system. We can take that log and we can run it on our own computer and see whether we then agree on the result of that computation. So replaying executions on a log that has tamper-resistant properties is also a fundamental attribute of these kinds of systems. Now, logs do exist, as far as I understand, inside database implementations, but they are considered more or less an implementation detail. They're not really considered a part of the abstraction that the database exposes, as far as I understand. But here, this log is very central to the blockchain ecosystem. Yeah.
Question.
Yeah.
How did this conflict with your first item? So what if I dispute not the log, the data, but I dispute the code?
Yes, actually, that is also very important. So it is very important in the log somehow you have to also agree that we are all executing the same code. It's extremely important. So there's this bootstrapping problem that you also have to solve. I'll have allusions to these kinds of problems that pop up in the rest of the talk also. Yeah. So you need to have code agreement so that the reasoning that I did in my mind, or using a verification tool that this code will have the same outcome, is valid for me and it's valid for you also, because we're using the same rules of logic. And then the execution that is generated from that code, because of the tamper-resistant nature of the log, we're going to make sure that you get the same execution and I get the same execution. And therefore, we will ensure that your truth matches my truth, so to speak. Okay. So any more questions about the first slide? Yeah.
Yeah, just a small clarification about the third point. So you mentioned that log is more of an implementation detail.
Inside database.
Yeah. So the way I look at log in a database is that, so the log essentially lets the database provide durability to the user. Mm-hmm. So in some sense, I think the blockchain is adding an additional dimension to that, which is tamper-resistant.
That is correct, yes. So it is certainly used for providing durability, because when you replay the log, you reconstruct the data or the computation, right? But this particular issue that it enables auditing in the case of dispute, it was never really an issue, right? Because database applications tended to be within a single company. What is this dispute, right? We all know each other, right? Okay. All right, so here's how I think about the programming model for blockchains. There's a repository of state, okay? And then there are messages coming into this repository. So each message has a message name like M1, M2, M3, M4, and then it has some parameters given by these values. Now each message is going to have a message handler. And when that message is received, that message handler executes here and updates the state. Then the next message is taken from the input queue, and then again the same process repeats. So, so there's a couple things that are very important here. One of them is that these messages, they may be coming from, from entities that are geographically distributed. But from the point of view of the programming model, it's as if there's an input pipe that is serializing them all. So they execute one at a time. And they execute indivisibly. So either the entire message handler executes or none of it executes. This is like the transactional semantics. Furthermore, these event handlers are deterministic. So this this I think is not foundational that they be deterministic, but it is certainly a very, very convenient feature to have. Because if you guarantee that the event handlers are deterministic, then you can get replayability of the log just by recording the input sequence of messages, these messages and the values. But if it is not deterministic, these event handlers are not guaranteed to be deterministic, then to generate a replayable log, the sources of non-determinism inside the event handler would have to be logged also, which will tend to make execution more expensive, more complicated, and so on. Yeah.
Proof of work mechanism works well. Each of the single node can have reliable sources to reach to get all the information on already consensus.
No, I didn't follow that. Repeat that, please.
So this is assumed that the proof of work mechanism works perfectly well, and each single node sort of can have a reliable source of the history of the of the blockchain.
Yeah, I mean, what I'm proposing here is kind of independent of whether you're using proof of work or not. Even if you took proof of work out of the picture, and let's say that you are using classical mechanisms of reaching, say, consensus on this extensible log, right? Even then, the same programming model would apply. With proof of work, there is this issue that temporarily there could be forks, but they have these sort of rules of the game where you say that, okay, we're watching out for your transaction, make sure that it is like 6 transactions or 6 blocks back in the history, because after that, it's unlikely that there would be a fork. So you can just take a prefix that is at least 6 or whatever, some number of blocks back. Yeah. Okay. Any other comment about that? Okay. So that was the programming model. Now, of course, you can implement this programming model in many different programming languages depending on your taste. And I think that, well, there are certainly many programming languages that are people are trying to use right now, and I think that that's how it's going to be. I don't think that we are going to arrive at a universal programming language here. So it's not going to play out like SQL in the blockchain world. I don't think so. But that's an opinion. Yeah.
This only exacerbates the question of trusting the programming code, because now if we have to agree on a trusted code, and this code can be written by different participants in various languages, how do we agree that these are implementing the same code?
So I think that, yeah, that's a very good question. So having many different programming languages doesn't necessarily mean that a particular application is implemented in different programming languages. You could still have a large pool of many blockchain applications where these applications maybe are written in Solidity, and these applications are written in a different language, and so on and so forth, right? I think that, but I mean, your question still remains. I think that there's an enormous cost to building tooling for a language. The more advanced the tooling you're trying to build, the more the cost. If we believe that blockchain programs deserve a lot more scrutiny than ordinary programs, like verification and so on, then that means that the cost of tooling is going to be higher, because then you have to implement verifiers also. So I think that there's a tension there. People want language diversity and they want convenience, because developers have different backgrounds and developers want to be able to leverage their background. They don't want to have to learn this one particular language. On the other hand, if you want advanced tooling, then it's very expensive to build advanced tooling for lots of different languages.
Do you know how Bitcoin solves this problem? So I know they update their software all the time and their protocols. How did this happen? How do people agree on a new code base?
So the blockchain is not extensible from the point of view of the programming language. The blockchain implementation, I don't know what language it uses, but that's not what I'm talking about. I'm talking about the application on top of the blockchain infrastructure, right? As a concrete example, I think Ethereum is probably implemented in C++. Is that right, Shuma? Two backends, right? So Ethereum, which is the most popular general purpose blockchain system that supports general purpose VMs, it has two implementations, one done in Go, one done in C++. But on top of it, the most popular language that is currently exists is Solidity, which is a completely different language, but that's for a different purpose. It's not for implementing the infrastructure, it's for implementing the application on top. Yeah.
So we can get the discussion more specific. So I think this is a really interesting question. So I can give you two examples. One is Solidity. Basically, you have all your favorite language construct, the control flow, the for loop,
Yeah.
right? And this is the Solidity is compiled to a bytecode,
Yeah.
and is executed in the server virtual machine.
Yeah.
And the other approach, which is try to sort of embed the smart contract with the other language, like for example, Go,
Yeah.
like the Hyperledger.
Hyperledger, yeah.
And if you think of a developer point of view, how you develop the smart contract, it's actually pretty awkward because you kind of, so for the simple stuff, just send one function call, the payment is fine. But if you need to define some control structure and you want the deployed code, you basically you have two choices. First, you have a Go runtime in your whatever blockchain virtual machine, which is not the thing you want to do. And second, if you still want to compile the Go code to the bytecode, you are essentially sort of have a weird way of building ASTs or all these weird control structures within Go. So
is the Go code actually compiled to bytecode also in Hyperledger, to the Ethereum bytecode? No, they're not doing it, right? Okay.
Yeah, but then the programming experience is not super cool. I mean, I think one way is you build some containers or some like a sandbox to isolate the execution, but then it's like you basically it's kind of like put all the language runtime of the language you are embedding the smart contract into your dependency or the trust.
That is correct. Yeah.
So I don't know what is best solution here. But
Yeah.
it seems that
Yeah.
at least to me or to the developers, the current way of Ethereum handling things seems much nicer.
Yeah. What Shumo is pointing out is that there is this tension between programming convenience and what is the size of your trusted computing base. Oftentimes, programming convenience occurs because you have a very, very extensible runtime in which you can drag in all sorts of crazy libraries, right? If you look at .NET, for example, or you look at C++, or you can look at Java, right? All these runtimes are highly extensible, and you can just pull in whatever code you want. They have things like reflection. On the other hand, if you look at something like the Ethereum virtual machine, it is buttoned down. I think you cannot really extend it. Maybe like once every 2 or 3 years, they will pass some legislation in the Ethereum Foundation to extend it, but it is completely buttoned down. What are the set of instructions that virtual machine can execute? So that makes it inconvenient. But on the other hand, the nice thing about it is that your TCB, your trusted computing base, is fairly small. Yeah. Okay. So we have many programming language contenders. No doubt the most popular one right now is Solidity, which is I would think of it as kind of similar to an object-oriented language like C# or Java. So you have classes, and they're called contracts. In Solidity, you can create instances of those contracts. So they're like objects, and then objects have methods in them, and then you can invoke methods, and a method can invoke another method in a different object, and so on. So the way execution works is that these transactions that come in, they correspond to a call to some public method in one of these contract instances. And that method call starts executing, and during its execution, it can call other methods on other objects, and eventually that entire execution finishes, the call stack becomes empty again, and that's when the transaction finishes. And then the next transaction comes in. So, so that's the Solidity, and I think Go is similar. Then in some other blockchain infrastructures, they're using Java and its derivatives. Then there are these other languages that I would classify as workflow oriented. So here the programming model tends to be closer to state machines and then communicating state machines. Oftentimes business applications are like workflows. So imagine that I'm selling a car, or I'm transferring some money from my account to your account. So your workflow starts in some state. Okay, I have given my I've made my car available for you to buy, and then you make a bid, and then the bid succeeds, and then you move to a different state where now it's it needs some reconciliation, and then maybe the bank approves. So you go through lots of states. So these business applications tend to favor workflow-oriented languages, and there are several contenders there also. I worked for many years on a programming language called P. It has been used to develop large workflows in device drivers and in distributed systems. There's also Logic App, which is another language supported by Azure. Then many years ago, there was a BizTalk server inside Microsoft, and it was supporting this business process execution language, things like that. So no, there is not much clarity at the moment. I think we'll need a few years for things to settle down here and figure out what languages people prefer. It's going to be some kind of compromise between convenience and minimization of the TCP. In any case, I think the verification capability is highly, highly desirable. I think given the nature of these applications, they tend to be high-value applications where there is, financial transactions are involved, or you're interacting with the physical world. Providing static guarantees or even dynamic guarantees is going to be useful, and if languages are able to support it, I expect that's going to be like a winning feature to have, not just convenience. So we take a closer look at verification. So static functional verification would be fantastic, but people who are familiar with the challenges of program verification, we all know that automatic verification is undecidable in general. Even if you have, for example, the simplest thing I know is that if you have two integers, unbounded integers, and loops, you can already encode a Turing machine with that, right? And if we look at the most popular language that we have on blockchain, which is Solidity, right? It certainly allows you integers. Well, we cannot really implement unbounded integers, but an unbounded integer is a very nice abstraction to have, and that's the abstraction that Solidity is trying to provide. You have unbounded data structures and lists and maps and things like that. So automatic verification is going to be undecidable in general. Now note that that is true even if you make sure that each event handler is written in a Turing incomplete language. So for example, in Solidity, because of all these gas restrictions, you know that every execution is going to terminate. And maybe you can even come up with some requirement that the execution terminates in a certain amount of time. But that doesn't necessarily mean that the verification becomes decidable, because there's a loop on top of those event handlers. And so you can have an unbounded number of requests coming in. Maybe each request terminates in some small amount of time, but with those unbounded number of requests, your state can keep expanding potentially, okay? And that execution is going to be unboundedly long. Yes?
But for each of those
executions you need to provide more gas, right? So there is a bound on that.
I mean, there's a bound only in the sense that the total amount of gas in the world is bounded. But that's not a useful abstraction, right? You provide a small amount of gas to one particular transaction. But I don't think that applications are written in a way so that you say, this doesn't matter how many transactions I run on this program, the total number of gas is bounded. You don't try to bound that, right? Yeah, so so even though these programs are not that big, so you would expect verification would be easy, but I still don't think that fully automatic verification is going to be that easy. Now that makes life very tough, because if you don't do fully automatic verification, then you need to resort to things like invariants and interactive verification. And most engineers are not exposed to that. So who's going to write these kind of applications if you want to have that kind of certainty with respect to functional properties? Perhaps we need to train a new class of engineers, like verification engineers, the way you were talking about earlier. But certainly in the short term, what could be very valuable is if we can do runtime enforcement of critical properties. That way, you know that, well, your executions that are being generated at runtime, we are checking that they don't go out of the safety envelope. If they start going out of the safety envelope, then we abort the execution. So sometimes your program may stop making progress, but at least it's not going to do something crazy, right? So it's not as good as static verification, but it's better than nothing. And yeah.
It's kind of interesting because the blockchain itself already proved, or you can view it as a runtime verification for temper evidence, and already preventing double spending. So, and also there would be, I mean, I think it's another MSR work, the Concerto, kind of proof. It's a key value store which give the like a crypto proof as a sort of verification of the existence of and tamper resistance, this data.
I would say that tamper resistance is a lower level property. It's a property of the blockchain infrastructure.
Yeah, it's much lower.
Yeah.
It's actually interesting. Can we sort of leveraging this ability provided by the lower level and trying to do more like expressive invariants or more things?
Yeah, it could be that, you know, the so you spoke of Concerto. I think Concerto is a runtime enforcement technique. So it monitors the execution and spits out a proof that that execution satisfies certain properties. If that kind of mechanism was built into the platform, that could make it much easier to monitor and evaluate executions of even applications on top. Yeah. Okay, so couple slides about what I consider, you know, are some programming challenges that we should pay attention to. Okay, so so certainly distributed execution is a challenge. There's nothing new here. All distributed programs are difficult to deal with because everything becomes complicated when you have a program whose runtime is distributed. So deployment is complicated, monitoring is complicated, debugging is complicated. In addition, here we are dealing with these logs, and we have replayability concerns and so on. So checkpointing and error recovery would need to be built in. In case that there's a dispute and some transactions that were earlier quote unquote committed, they have to be rolled back, then you have to deal with issues like compensation. Industrial database systems deal with all these challenges. I don't think that these challenges will continue to remain even in blockchain systems. These are non-trivial problems to solve. Some newer problems that pop up when you are dealing with the blockchain applications, I feel, are things like so we are doing secure multi-organization calculations, right? So the main, if for example the application is within a single organization, that probably is not a blockchain application. Usually you need more than one party who does not really, where the different parties don't really trust each other. So when you want to implement a secure multi-party, multi-organization computation, you need to make sure that all the transactions that are being submitted into the system, they are signed by the user identities. So to sign it, you need some kind of keys, and managing identities and keys is a big headache. Organizations, they begin to expect, based on their experience writing business applications on top of a database, that these headaches I don't have to solve, right? Today, for example, when you write an application on top of a database, what happens? Well, a user signs into the application at the very beginning, and at that point, the user is authenticated. Now you don't have to worry about authentication over and over again. But in blockchain systems, every transaction that is entered has to be signed. So the management of these identities and keys is a headache. Okay. Okay. So another problem is that so the observed state lags behind actual state. So this is actually probably a problem even in database applications, and something maybe you guys can comment on. So when I submit a transaction, I don't have a lock on the database. I just know that my transaction is going to be serialized eventually, right? But it could be that another transaction got committed before my transaction, and that changed the state, right? So I have to write the code of a transaction has to be written in a defensive manner, so that it has to internally establish its preconditions before it makes any updates. And if the preconditions cannot be established, then it should just abort the transaction. So this is something that it's a programming practice that programmers have to deal with, and you can make errors there, and so maybe you need error checkers for making sure that you're not screwing this up. Okay. We also need access control on top of these identities. So when you have transactions, given a particular state of the application, some users are allowed to do certain operations, and some other users may not be allowed to do some operations. So oftentimes you need this kind of access control. You need to implement that for the security of your application. The next point is something that Dan was talking about. So you need secure application bootstrap and version update, right? So if the parties cannot agree, are not assured that the code that is running is what they agreed upon, then all bets are off. So you need some way of ensuring that the code that the parties agreed upon is the one that is actually being executed, that they're not executing different code bases. And again, you have to solve that problem if you want to update the application in any way, right? So final thing is that the cost of a programming mistake is likely to be high, something I was talking about earlier. So this is, I guess this is good for verification enthusiasts, but it's bad news for building the blockchain ecosystem, because what that means is that we are going to demand more of the programmers, right? And that makes it tougher to build a large ecosystem of programmers and applications, Okay. So any comments about that? I'm moving to the last part of my talk.
How the burn update could possibly better handle?
How what can handle?
you said, I totally agree that, for example, update the version of the smart contract, it's, or like somehow you want to change the contract and with the already serving, that is already serving user seems very hard. So
Yeah, so I don't know. Some of them I have some. I'll tell you what we are trying to do in AppBuilder. So we have some ideas about some of them. Yeah, but the number of problems is too large. Yeah. Okay, so we are working on this AppBuilder project in Azure right now. So the goal of AppBuilder is to raise the level of abstraction in blockchain programming. So this particular project was born based on our experience. So what we did first in our team, this is even before I joined the team, is that we created these templates which allowed users to quickly deploy a blockchain network on top of Azure. So they can say, hey, I want you to give me a 5-node Ethereum network. Just deploy it, connect all the nodes together, and give me an endpoint so I can start submitting transactions to it, right? Why would people want to do that? Well, people want to do it because sometimes you are building a business application, and for privacy, confidentiality reasons, you don't feel comfortable using the public blockchain network. So you want to play around with it, and you would just rather do it in the setting where it's a hosted blockchain that is shielded. Nobody else can access the state in there, and only you can submit transactions to it. So that's why people like that. So we had these templates, and we saw that people were struggling. We automated the part of deploying private blockchain for them, but building an application on top of it and making sure that the application runs and it's making sense, it was still very hard. So it would take them on the order of, like 6 to 8 months to get to a point where they're able to run some useful workflows in their application. We wanted to cut that down dramatically. So that's how AppBuilder was born. So all the headaches that people were facing, we wanted to automate a lot of those problems to allow them to get to a useful point in their application flow, say within a month or so, much faster. So what are the key innovations here? I would list a few, So first thing is that we have an application model based on workflows. So a lot of our clients are businesses. And as I mentioned earlier, the kind of applications that they are writing, they have a natural workflow abstraction. So we wanted to support that directly. So this application model based on workflows is, you can think of it more as a specification. It does not require you to implement your application in Solidity or in Hyperledger or whatever. We want to give you the flexibility of targeting whatever blockchain you want. We should be able to plug it in, okay? Second thing is that we are providing role-based access control for these workflow transitions. So in these workflows, you have states. I'll give you an example later of what these workflows look like. So you have states, and then based on user actions, you make transitions from one state to another. So what we provide is a way to implement access control on which user is allowed to take a particular action that moves a state from one state to another, takes a transition from one state to another. Third thing is that programmers, applications, don't have to worry about identities. So they don't have to worry about blockchain level identities. They will have your organizational identities, such as those in, say, Azure Active Directory. And you just register users based on those IDs. And the system automatically takes care of provisioning blockchain identities that are backing those user level identities. And then all the secret keys, that they are going to be managed securely. So you don't have to mess around with it. We'll create keys for you. And we're going to store them in the standard services that are used inside Azure for storing secrets. And we will sign transactions transparently. You don't have to worry about all that. Okay, so I think of what AppBuilder is doing is basically providing you middleware that makes it easy to ingest, deploy, execute, and monitor applications. So here are like the main components that are getting pulled inside AppBuilder. So you have a blockchain for executing applications. The first blockchain that we are supporting is Ethereum. Based on demand, we may even extend our support to Hyperledger. But Ethereum we are definitely supporting. There's a SQL database for storing state. Now, I use the word caching, but that's probably not the right thing to say. Caching implies that you have an accurate view of the state. This is not an accurate view of the state. This just means that this is a stale view of what the state of the application was. It's easily queryable so that you can make appropriate decisions in the UI about what is the next thing to do to the application, right? So basically, there's an agent, there's a daemon sitting there that continuously reads the state of the blockchain and updates it in an easily consumable manner in a database so that it can be easily queried. So that way, front ends don't have to go mess with blockchains. People typically don't know how to mess with blockchains. We just make the data available in a database so that front ends can be written in the normal way. So we have Azure Active Directory that gets pulled in for managing identities and authentication. Okay. So we use federated AD that allows you to import inside a single AD tenant identities that are coming from multiple organizations. So that's how we would like to be able to create multi-organizational blockchain applications. Key Vault will be used for key storage and transaction signing. And then there's a few other things, for internal system management that are not really visible to the application. So these are the main components inside the AppBuilder implementation. Okay, so I wanna conclude by telling you a little bit about our app model based on workflows. So an application is a collection of roles and workflows. Okay? So a role is a set of users, and the app administrator can dynamically add a user to a role or remove a user from a role, right? There's also a separate mechanism for registering a user in the system. Only a registered user can be added to a role. Okay. So these are just sets of IDs. Yeah.
Is the user's management external to the blockchain, or just you update it? There's a way to you write the smart contract in such a way to whitelist users, right? Is this outside the blockchain or inside the blockchain?
So yeah, good question. The set of all users registered in the system is outside the blockchain. Okay. But when you have an application that has certain roles associated with it, those roles are part of the application state. The contents of those roles is part of the application state. So that should be part of the blockchain state. That's kind of important because you're going to use the value of those roles to implement access control. Okay. Okay, so a workflow is an abstraction of executable code. Okay. So it has properties, like properties in a class, functions, states, and transitions. So transitions take you from one state to another. Okay. So each transition is annotated with the name of a function, right? So it says that, okay, if you want to make a transition, then this function must be executed. Now you look at the signature of that function, it tells you what are the parameters. So now in the UI, you can ask the user to supply that parameter. So when the user supplies that parameter, you can execute that function, and then it makes a transition from that state to from the source state to the sync state. Okay. A transition is also annotated by an access control mechanism. So the access control mechanism specifies which user is allowed to execute this transition. Okay? So that is determined by using set membership in some role. So for example, if there's a role defined, then you can annotate that transition with that role, and that is saying that any user who is a member of that role is allowed to execute the transition. Let's take an example. Let's take a look at an example. So this is an asset transfer application in which there is a seller, he's selling some object, and then buyers come in and they bid for it, and eventually the transaction is completed where the buyer makes a payment and then the seller moves the ownership over to the buyer. So the execution starts over here. So the owner of this asset, he creates an instance of this workflow to start tracking the transaction. So the workflow constructor is invoked, right? And it has some values that are passed to it that are relevant for the scenario, like the description of the object and the suggested price. Now, restricted to seller. So there are two roles in this application, seller and buyer. And Alice and Bob are registered users. And at some point, the admin added Alice to the seller role and added Bob to the buyer role. So at this point, we pick up the execution. Yeah.
Which entity is a public key associated to? Is a public key?
Yeah, that's correct. So when a user is provisioned in the system, it creates a public and private key pair to the associated with the user. So there's a public key associated with each user.
And if the user has multiple roles, is that the same public key?
Yes.
Or? Okay.
The user could be in many, but the public key is the same. Public key is associated with the user, not with its membership in any role. Yeah. Okay. Okay, so the construction of this workflow instance says it's restricted to seller. So what this is saying is that only a user who is a member of the seller role can start an instance of this workflow. Okay? And then the constructor executes. So the workflow specification doesn't say anything about the implementation of the constructor. The idea is that you implement that in some language. So I mean, it's again an interesting area of research. You know, what are appropriate languages for implementing workflows, right? So you know, but whatever that implementation is, it will probably going to set description and suggested price and a field called instance owner. So this description property will be set to this description value. This suggested price would be set to this suggested price, and this instance owner is going to be set to the seller, the user who created an instance of this workflow. So this instance owner is a field inside the workflow to which gets set in the constructor. It will become important why we need this field. Okay, so now we are, the workflow is in this state where the goods have been listed. So now at this point, the workflow can accept a request from buyer, bids from buyers, right? So a buyer can now make an offer with an offer price. Now this transition is restricted to somebody who is in the buyer role, okay? And this, when you make this, when you execute this function, it sets the offer price property in the workflow. Then we move to offer placed. Now this is very interesting because at this point, we can accept the offer and move to the offer accepted state. But note, who is allowed to accept the offer? We cannot say anybody who is in the seller role can accept the offer. We want to make sure that only the guy, the user who created the workflow instance can take this transition. But we can do that because we stored his user ID in the instance owner field. So now we can say that this transition is restricted to the particular user whose ID is stashed in instance owner. and he can move the state to offer accepted. Okay. Yep.
I think what this means is that since you're only doing the role checks at each state, if there was a change in membership while the transaction was going on,
Yep.
that could be a problem. I guess
So, role. That's why role membership change is also a transaction. This is actually a question that Shuma was asking earlier. The registry, to make this bulletproof, the registry that contains the membership of each role must be part of the state of the application, and you have to make that part of the updates to it part of the transaction also. Yeah. So that's what we want to, where we want to get to. Yeah. And that is the last slide of my talk. Questions? Yeah, Ras.
So if you have to verify, what is the scope of verification? Would you like to understand that this protocol is well designed in the sense of having no loopholes in it, not loops, loopholes?
Yeah.
Or do you only care about, given protocol at this level of abstraction, is it correctly implemented?
Yeah. I think both of them are important. If, for example, let's say that the access control, right? If the code implementing the access control is synthesized, then we know that's correct by construction. But if we did not generate that code, and if we told the designer, this is the workflow specification, you go and implement it, then we have to go, and the verification problem would then be, go and make sure that the implementation actually adheres to this workflow, this access control specification. But this is, I think, is the bare minimum, right? I can easily imagine that there would be other more functional safety specifications and progress specifications also, right? I mean, a bad thing I can imagine, this has actually happened in some contracts in Ethereum. They basically get deadlocked. So they reach a state where no action is feasible, and there's some money, they call it, this is funny money, Ether is sitting there. And at this point, that Ether is kind of locked in the contract, because no matter what transaction you submit, it cannot succeed. You don't want that to happen also. That's a kind of progress specification. There will be all sorts of other functional safety specifications also, I think, in non-trivial contracts, like realistic contracts. This is the bare minimum, I would say.
Such specification, other specifications stating intent of the transaction. Here you're gonna sell something and transfer assets. Is there a higher level language for stating that?
Yeah, I don't know. I don't know about that. Yeah, I don't know about that.
Compliance with government regulations could be a major killer app here, right? You need to check that the transaction you're doing is compliant with so many rules.
Yeah.
You're not allowed to sell, guns to the foreign country unless you have approval from the government. All this needs to be checked.
Yeah, that's correct. So that's correct, yes. So in general, it's the same problem that we have seen in program verification over and over and over again.
The abstraction is just so much higher level.
No, there's nothing new. No, I've seen all these things many, many times before. Basically, the problem that happens in a lot of this verification is that you have some code, right? You have some idea, yeah, it's supposed to do this, right? But verification cannot start until you express the same thing in two different ways. Because verification means that you're checking this version of what you were trying to do with this other way of representing the same thing, and then you check for conformance between them. And oftentimes, the magic of specification is that it gives you a compact way of expressing your intent in a slightly different way. And then you can begin to do verification.
Slightly different, right?
Yeah, ideally more than slightly, for sure.
So clearly you face the problem of how do you make programmers verify all this. So if you could picture or design and deploy a calamity that would make them adapted right away, what would that look like?
a calamity here, like some calamitous result that the program was wrong, you mean? I'm afraid I don't have enough experience with applications and customers yet. But that is definitely something that is on the cards for me. I want to spend, I mean, I've been working on the AppBuilder infrastructure, but one of the things I want to do in the next 6 months is work a little bit with applications and customers to understand what is it that they're really trying to achieve with the blockchain.
Thank you, Les. Thanks. Thanks for coming over.
Yeah. Thank you.
We have to run, all of us, because there is another talk, a colloquium at 3:30, and
Okay.
everybody
Sounds
goes
good.
away.
Okay, all right.
Thank you so much. This
Yeah.
was a really nice talk.
Okay.
My copies.
Sure.